something like that. This is VS, okay? So to know what it actually is, or what its equivalent circuit is, what we have done last time, we will do it again, which was we will draw equivalent circuit within this amplifier, okay? So that was our positive or negative. That was our RI. And that was our R naught. Okay. And if we compare it with the circuit that we have drawn for a unity gain, then it will be this. Okay. So that's the circuit if you compare it with the equivalent circuit of this amplifier. Okay. Okay. So now I just should not do this yet. So now let's draw this circuit in a simpler manner, okay? Let's see what this circuit is. So what I'm doing is RI is connected to R naught, A naught V in, which is connected to ground. And then this is connected to VS. This is your R naught. Okay, and as this was your V naught, so your V naught is across your R naught. Does this make sense?
Yeah, it makes sense.
Do you have any question about that? How we drew this circuit? This was what our V in that. So that's our equivalent circuit for unity gain amplifier, okay? But let's try to solve it and let's see what this is actually is. So you can see that there is a common ground here. This is a common ground, right? So it means that this circuit is forming one total loop, and there will be a current that is flowing here. So if we say that the current that is flowing is I, so we will write the equation, okay? So let's write the loop equation in this case, okay? So that will be minus Vs minus Vs plus IRI plus IR naught plus A naught Vn. Okay, so that's my equation where my Vin is IRI and my V out is V naught or V out is IR naught plus A naught Vin. Right? Is this okay?
Yes, yes.
Okay. So I want to solve for gain, right? Because in op-amp, the most important thing is the gain. So what I will do here, I will say solving for V naught by Vs. So I will try to find the equation in which I can just find V naught by Vs. Okay, so for that, I want to simplify this equation first. Let's see. So my Vs is minus IRI minus IR naught minus A naught V in, or Vs is IRI plus IR naught plus A naught V in. Okay, so I divide equation for V naught by equation for Vs. Okay, so this equation divided by this equation will be V naught by Vs is equal to IR naught plus A naught V in divided by IRI plus IR naught plus A naught V in. So I can take this common. Right? Is it clear? If you have a question, if you think that it's not clear, you can ask, okay? So we wrote equations for the one loop, and we want to find V naught over Vs because we need to know what is the gain of the amplifier, right? So, okay. So this will cancel
go
out.
up a bit?
Yes?
Please? Like, can you just scroll up a little bit, please? Okay, thank you.
Okay. So this will become okay. Okay. So in op-amp, I will talk about it again, but we need to know what is the ideal op-amp configuration, okay? Which resistances should be higher and which resistances should be lower. So that understanding will help us to know what actually purpose of op-amp is, okay? So previously we said that R naught should be lesser than Ri, and which makes it V naught by Vs is equal to 1 plus IRI. Why we are saying that? We discussed it last time, but we will discuss it again, okay? So hang in there. So IRI, we are saying R naught is lesser than Ri, which makes it A naught Vn. IR naught plus A naught Vn is approximately equals to A naught Vn. So V naught by Vs is equal to 1 plus IRI. We know that V in is this thing, IRI. So we will just replace this here. And this will become okay. So as we know, we have defined it before, that A naught is very high number, or A naught tends to reach infinity. So if A naught is greater than 1, of course, then V naught by Vs will be approximately equals to 1, which is the ultimate goal of unity gain amplifier or the buffer, okay? So this is the unity gain amplifier is actually V naught by Vs is approximately equals to 1. And the configuration is, in its configuration, we just have to connect a wire from op-amp's negative input to the output. Okay, so that's the thing that we need to remember. Okay. Okay. Now we again want to talk about what we are saying about ideal op-amp model. Okay. If we just see our previous lecture about op-amp, I just want to recall what we have done before. So if you see in this op-amp model, this was the model we have defined. And in this model, we have said that if RL is equals to infinity, that there is no output voltage, then your V naught over V in will be equals to A naught. And if your I or out is 0, then we said that why we need to have R in very much higher, right? R in should be higher because we want it to be a constant gain, right? We want op-amp to not to be dependent on different resistors value. That's why we said that R in should be greater than RS, and RL should be greater than R naught, which makes us to realize that R naught should be smaller and R in should be greater. Okay, so we need to remember these things. So if R in should be greater, then it means that if it is really greater, then it means that very small current will flow through it, right? So that's what we need to remember, that these things, that this should be greater and this should be smaller. Okay, these are the very main important things. What makes it, what difference it will make it to our circuit? Okay, let's see. Okay, so in ideal op-amp model, we said that A naught tends to reach infinity, Ri tends to reach infinity, right? Because we said that Ri should be really, really higher, because it should not be dependent on Rs, okay? And when these things will be infinity, if you see here, then it means that if your Ri is really large value, then the current through it will be very small, right? So if your current through it will be very small, it will make your V in approximately equals to 0, and your input current also approaches to 0. Now, what we have defined V in as, V in was the difference between positive terminal and negative terminal, which was V2 minus V1. If this is equals to 0, it means your V plus is equal to your V minus, or your V2 is equals to your V1. So for ideal op-amp, you expect that the difference between the terminals of these terminals will be very small. And you call this as error voltage. So V plus minus V minus is also represented as VE. So we can say that VE should be approaching towards 0. Okay, so we really need to know that what these things mean. Okay, so is it clear that why we have done that for ideal op-amp model?
I missed the part about VE. Is VE just V in, basically?
VE is V in. Don't
Okay.
confuse it with VS. VS is the source voltage. V in is the voltage drop across resistor, right? And
Yeah.
because your current is very, very small, that's why it's actually practically equals to 0. And your difference of the voltage is approximately equals to 0. Okay?
Okay.
Okay. Why we are doing all this? That's an important question, okay? Why we are assuming so many things, and why op-amp is even created? We need to know these things. So first, we will think about unity gain amplifier again, okay? And then we will try to deduce our, what you should say, conclusion, okay? So let's think about unity gain amplifier again. So if we apply our ideal op-amp model on unity gain amplifier, so which means that what we are saying here is that there is very little current here that is passing here. And because the voltage across this drop is 0, so this terminal is practically IS, well, VS, okay? So as they both are connected through wire, so your V naught by VS is approximately equals to 1 in your ideal buffer situation. Buffer or unity gain amplifier. Now, if you add a load resistor across this amplifier, let's say this is 1 kilo ohm load resistor you have. Okay, so what will happen then? Okay, so you will have I naught equals to V naught over RL, right? And you can see that your IS is not dependent on your I naught, okay? This thing is tackled by op-amp in itself. So I naught is getting its current from the power supplies that are energizing the op-amp. It's not getting current from the input source. That is the difference in case of the op-amp configuration. So when we are connecting it as a unity gain buffer or amplifier, you can see that input current is approximately equals to 0, but still you are getting an output current. Why is that? Because it has external power supplies that are connecting to it, which are energizing op-amp, and they can produce I naught. So it's not like that we are not giving it something and it's producing, because it's against the law of conservation of energy, right? So the power supplies which are energizing op-amp are actually giving us I naught. But why we are taking I naught just from power supplies? That's an important question. Why we are not just trying to connect VS with RL to get the output voltage, right? Why we are doing that? What do you think? Sorry, this is RS here in real circuit. What do you think? Why we are not just doing this? I'm just connecting it like that. So if this resistor network is RL, why we are not just doing this or get the voltage V naught across RL? What do you think? And why we are connecting op-amp in between? Because it's right now it's gain is 1. Okay, so the answer is that you already know, or we have already done this, that your V naught here will be VS minus IRS, which means your V naught is dependent on your input current, right? On this current, or it will reduced by RS, the internal resistance, right? So it's uncertain situation that we don't know sometimes what is RS is, and our V naught can change. So to avoid that scenario in which your V naught should not change, V naught should not be dependent on your source voltage. That's why we always try to put op amp or the buffer in between them, because op amp is actually isolates the source from load. Do you understand this? Why we are not using simple resistive network to get the output voltage? We are putting a network that will isolate the source voltage from the load voltage. So that's why we are actually saying that this unity gain amplifier produces constant output voltage for the RL. Does this make sense?
Yeah, it makes sense now that you explained it. Thank you.
Yeah, so that's why we are trying to avoid this scenario, like we were saying in voltage divider when we were doing ENG212, that internal resistances can be uncertain situation, right? We will do experiments regarding op amps, so that will make things more clear. But it's really good that we are learning theory now, so it will be easy to apply them in the practical world. Okay, so if it looks like that I'm not, getting it or something like that, the things will become more clear. So right now you just try to absorb what information is, like whatever you are getting, right? But once you are doing experiments, you will learn why op amps are important, because I know it's hard to process that how input current can be zero. And if input current is zero, what's the purpose of getting it at an output, right? But the idea is to remove the dependency of the output load voltage to the input or the source voltage. Okay. Okay. So now we are talking about another configuration. Last time we talked about inverting op amps. In this lecture, we will be talking about non-inverting op amps. So if you remember, in inverting op amps, we were putting our input voltage at negative terminal. And here we are putting our input voltage at positive terminal. That's the difference. So this is RF feedback resistance, or R2. Okay. And this is our V naught. Okay. So V plus is equal to B minus. And you know that this thing is here. and I minus is equal to I plus, implies I negative is equals to 0, makes us think about that our V negative is equal to V positive is equal to V in. So we want to make the case that this V in is the here V in as well. Okay. So let's write the KCL equation. Okay. Okay. So I can just write it V in by R1 plus V in minus V naught by R2 is equal to 0, right? I write KCL equation here. Okay. And then if I just write it like this, okay. And then in most of the cases in op amps, we want to know V naught over V in, okay? Another thing is you need to understand that A naught is a constant gain, but V naught over V in is what you get from the different configurations of op amps. So A naught is what is defined in data sheet. So when you will use some specific IC of op amp, you will see, oh, its A naught is, let's say 10,000 or something like that. But V naught over V in is what you will design using op amp. Okay. Yes. Okay, so it will R2 by R1 plus R2 by R2. So this is your V naught over V in's expression for non-inverting op amp. And you can also say that this is equals to 1 plus RF by R1. So which is R2 or feedback resistance. Okay. Another thing you can note it here is, so this is non-inverting op amp. For inverting op amp, you got V naught over V in is equal to minus R2 by R1, or this was the feedback resistance. Yes. So the important thing to realize here is this negative sign. So you see that in non-inverting op amp, even though we are saying in ideal case scenario, plus and minus are equal, V plus is equals to V minus, but still when you are solving for V naught over V in, you are getting negative in output. So that's why it's important. The positive and negative terminals are important. And that's why for non-inverting op-amp, you are getting a positive gain. And for inverting op-amp, you are getting a negative gain. Okay. So now we will see a difference between the ideal scenario and what you should say, equivalent circuit model that we are doing. Okay, let's see. Okay. So we said that our non-inverting op-amps configuration is this. This is V in or VS, okay? Okay. I should say that this is the difference between ideal gain and practical gain, or what, and finite gain. Actual gain, sorry. Actual gain, okay. So that's what we will need to see, what is the difference between them. Okay, so now I'm drawing again non-inverting op-amp and see that how, what expression we will get. So this was our R2, R1. This is our V0, and this is our VS. So we don't have RS here, but we are, instead of doing V in, we are saying this is our VS, okay? Okay. And the equivalent circuit model for this is, again, if we draw this like we do before, I feel that, or I find it easy if I think about the model and draw the circuit inside. It will help me to see that how the equivalent circuit model will work. Okay, but it's up to you. If you don't have to do that, it's okay. So VS plus minus V in. Okay, I know that there is a resistance between it, across which the voltage drop is V in. So right now I'm not drawing it, but I know it's there. So this is R1. This is R2. And here we are having R2, R0, and this is A0, V in. Right? Now, I just say that, oh, in this black box, the voltage drop is V in. Another thing I am saying that, as we know that R0 is very, very small. So I'm just drawing it as a wire. Maybe it can replace it as a wire. So I'm not trying to complicate myself, because if I include this in calculation, it will make the complicated expression. So I'm just saying that R naught is very small, assuming. Okay, so in this ideal model, in this model, okay, so I know that VS, one more thing I want to define here is that here I said that V1 is there. So V1 is equal to R2 by R1 plus R2 into V naught. Okay, if I just don't think about this right now, I'm just thinking about the outer circuit. Okay, then I'm saying that my V1 is equal to R2, no, sorry, should be R1. R1 by R1 plus R2 into V naught. Okay, so if you think that you're not understanding it, you can just stop me, okay? Is it okay? Is it good? Or it's hard to understand? Thomas? Sarah? Are you guys here?
I'm here.
It's a little confusing, but it's pretty good so far.
Just a minute. What?
It's a little bit confusing, but it's pretty good so far.
Okay, so what is the confusing part?
It's just all the components, I think, just after a little bit of time. Right now it's good.
Okay. Just. Nithya, what do you think? Is it good?
Yeah, I'm okay.
Okay. Derek, Kim,
Yeah, it's fine.
Yeah, it's good for me. Sorry.
okay. Okay. Because if you think that it's fine, it's fine. But if you really think that it's confusing, then you can pinpoint, okay, I don't understand this, what it is, or something like that. Okay, so V1 I found is R1 by R1 plus R2 into V naught. Okay, and I'm just saying that it could be beta V naught. So I am just defining for my ease that it is beta V naught, okay? So for this circuit, because now we are one layer ahead in terms of complication. Previously, what we were doing is we were just thinking the circuit and we were trying to solve it. Now we have to think about a block and we have to think about what is inside the block. So when we are thinking what is the block, then we are just drawing the circuit outside that block, right? So this scenario is this thing. When you just thinking about a block and the circuit around it. But in this scenario, you are thinking about what is inside the block and what is outside the circuit. So that's the two different things, right? And another thing is that in this case, in ideal case, you are thinking that your A naught is infinite. And here in this case, you are trying to solve for your A naught. I mean, you know that it's finite value. So there is a difference between them. And once I think it's just for this time that you need to think about what inside the block and what outside the block. Soon, when you will move towards the higher things, you just need to think about what outside the block. You don't have to think what is inside the block, because you already will understand that what the inputs are and what it means. So you don't have to worry about that. But right now, for understanding, it's important to see what's inside it. Okay, that's why we are doing this. So Vs for this circuit is, because we know that this is V1. So we have V in some element here, the drop here is V in and V1. So we are saying our Vs is equal to V in plus V1, because we have the drop here and here this point is V1. So our Vs is equal to V in plus V1. And okay, so and we know that our V naught over V in is A naught. Why? Because if we draw this V naught voltage is across A naught V in, and we can just say that V naught over V in is equal to A naught. Okay, so that makes our Vs is equal to V naught by A naught plus V1. And that will make it Vs V naught by A naught plus beta V naught, right? And this will make it V naught 1 by A naught plus beta, and this is Vs. So where this beta comes from? This comes from here that we have defined it before. So it will become V naught by Vs 1 by 1 over A naught plus beta, and it will become okay. Okay. Now our ideal gain was when we have collected gain here, this was right, and this was 1 over beta, because if you see this here, this was beta, that's what we have said, R1 by R1 plus R2, and this is R1 plus R2 divided by R1, which is equal to 1 by beta. Okay, so one by beta. So now we need to know what is the, okay, and one more thing is that they have used Vin and Vs interchangeably. Like you can see that here you are seeing Vs, and here you are seeing Vin, which is eventually equals to Vs here. So you just don't have to worry about why they have used Vs here, because they were using Vin plus V1 to simplify that, because in real world, Vin will not be equals to 0. But in ideal case, Vs is equal to Vin. That's why. So I should write, I think we have written it here as well. So this is equal to, for ideal scenario, V naught over Vs is equals to 1 by beta. Okay. So let's move. So what I'm trying to do here is, we know that ideal gain is different than the actual gain. So we want to find out the gain error. Which will be equal to actual gain minus ideal gain by ideal gain into 100. Okay. Actual gain minus ideal gain divided by ideal gain into 100. And let's say whatever actual gain was. So it was A naught 1 plus beta A naught minus 1 by beta and 1 by beta. So this will be equal to, right? If I just multiply with beta, it will be equal to A naught 1 plus beta A naught beta minus 1. Right? And I'm just thinking how they simplified it with the, let's try to do this way. Okay. So it could be 1 plus beta A naught beta A naught beta minus 1 minus beta A naught 1 by beta. So this will cancel with each other. It will become minus 1 by beta 1 plus beta A naught 1 over beta. So then it will become minus 1 plus beta A naught into 100. Do you know what I did here? I just, what I did here is A naught 1 plus beta A naught minus 1 by beta. I just took the LCM and then solved it, and it becomes easy. So this is your gain error for non-inverting op-amp. So the idea here is, you will know when you will solve the questions that you don't have to find new things that I have just did, like the gain error thing. But you need to know the configurations of inverting op-amp, non-inverting op-amps, so that when we will try to solve the problems, it will become easy. Right now, it's the theory, and it's a little bit confusing, but when we will do the problems, I think it will be more easier than that. Okay? So
What is the denominator there? What does that say?
1 plus beta A naught.
Okay.
Okay? So today I will stop it here. And from the next, I think, lecture, we will start doing problems, and it will be not as brainstorming than these 2 lectures. Okay?
Is there any chance you could scroll up a little bit? I missed that like middle formula. Thank you. That's good. That's good.
Dr. Khan, will you post this lecture so I can review it, or the notes?
Yeah, I will post all the missing lectures that we have now. Okay?
Okay, thank you.
Mm-hmm. So, yeah. Any other questions you have?